Howdy, everybody. How you doing? Hope everything's going well. We're here for day 15. Just as like a brief introduction, this one was a fun one. For me, I spent most of my time trying to like make the solution more concise, so optimize it a little bit in that respect. Um, but I had fun doing it, and I actually have run out of time, so I didn't get optimized as much as I'd like to, but I think I got it well enough to show it to you anyway. Love seeing your solutions too, and I love browsing the Reddit. So if you guys keep enjoying that, I'll keep looking at those things. So uh, let's get on to the problem. So day 15 is called Warehouse Woes, and the high level of it, I'm actually going to do both parts at the same time because you can solve both parts with one equation or like with one function. I should add that I didn't actually do that to begin with. Like when I was first solving it, I solved part one and then I copy and pasted part one and like modified it to work for part two. And then when I talked to you about making it more concise, it is when I was like, oh, I'm going to try and merge these two solutions. So but I am going to talk about both parts, okay? Essentially, you have a robot in a grid. So here's your grid, and here's your robot, and you're going to do a bunch of these moves that are shown right here. These represent, up, down, left, and right. And the idea is you're going to move the robot all around the grid. These hash marks are walls that can't move, and these zeros, or I guess they're O's, like capital O's, are boxes. And the robot can move the boxes. In fact, he can move multiple boxes. So if he were to right here and he were to move left, he would move this box over here, and then he would move over to right here, right? If he was up here and were to move left, he could move both of these boxes. They would both shift over one, and then he would be right here. And that's like kind of the trick of the puzzle is he may be shifting things multiple times. So they give you a smaller example and kind of step you through it. And you can see, like, for example, so right here, he moves it once to bring these two together, and then he moves right again, and it pushes those two over. Also, if he can't move, he just doesn't move, right? So you can see here he moves right, but the robot is unable to move more right, so it's just stuck there. But you can see then when the robot moves down, the robot can move like all four of these boxes, okay? And so your goal is to move the robot around, and when he moves boxes, move those move all the boxes that can be moved as he's moving around. It's not like we've had puzzles before where it's like a slider where it like slides it to the very far or back. It's just everything's moving one place, right? Everything that's in his way that's not a wall will move one place. So, said more concisely, he'll move all the boxes exactly one position that he can move of the ones that he can move. So you can see these examples, and they give you like an actual larger example for like a test case, which was actually helpful because like this simple case doesn't handle all of the positions. Anyway, the way to think about it is you're just going to move all this stuff around, and then you're going to do a GPS score based on where the boxes are. And I won't go into too many details, but you're just like multiplying the Y by 100 and the X by its value, and that gives you like the GPS of each box. If you sum up all the GPS values of all the boxes, that gives you the prediction. Okay. So that's part one. You can see like, you can imagine you're just like going through a grid, moving the boxes, and then you're done. Right. And I guess I can even talk about before I get to part two, like the way that I thought about it was very recursive in nature. So like if I have an empty space right here and then two circles and then the robot right here, like the thing that was going through my mind is if I'm the robot and I want to move this, I can just recursively say, hey, I want to move this, and then I can check its direction, right? If I'm always going this direction, I just make sure I'm always going this direction. So I say, hey, can I move this one? And it's like, well, I can if I can move this one. And eventually you say, oh, can I move this one? Yes, I can move this one. And so then it all kind of bubbles up, right? And so you move here, here, and then this goes right here, and then you get your at right here, right? And you just do that kind of for every direction. If you ever get like a wall, right? So like say you have a wall and you have a bunch of zeros and the robot right here, you're still asking yourself recursively, but eventually this one says, oh, I can't do that, right? All of these kind of said, yeah, I can do that, yeah, I can do that, yeah, I can do that, and then it moves, right? This one says X, and so that needs to propagate up to say, oh, you can't move. So none of this stuff can move, right? Obviously, if there's like, for example, this hash here, you could still move it once, you just couldn't move it again. So how does it change in part 2? Well, what they say is the map is actually twice as wide as it, and so each wall is actually represented by 2 wall blocks, and each box is now represented by these open closed brackets. So the box is like now 2 wide, and then and that's all that really changes. So like so it now looks like this, right? Whereas these were just occupying a single space, the boxes are now occupying 2 spaces. And the trick there is like when you want to move the box, you want to move it as a whole. And that's not hard for some cases, right? So in these cases, this doesn't actually change, right? Is like you actually, if you have the hashes now, and let's say you have this here, and then you have here, 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 and then the @ sign right here. And now you're asking yourself, you're going this way, you're still asking yourself, can I move this way, right? And so you can actually just traverse this and say, can this guy move here? Well, he can if this guy can move here. Can this guy move here? He can if this guy can move here. And this guy says, can I move here? And it's like, yes. So those, the yes propagates all the way up, and then it looks like this, right? It propagates like this all the way down. So like this one doesn't change at all, these left and right ones. They just don't change at all. And so that's like a key thing. Where it does change, though, is if you're moving up, right? So imagine the case where you're like this and you have the @ sign right here. Say these both are empty up here. And now you ask, can I go up here? And the answer is only yes if this one and this one can go up. So like you can think about like these pairs are linked to each other right here. There's like a link between these two, and they have to like go up together at the same time. So this one does work, but something like this would not work, right? Because you can't move this one up without moving this one up also. And that gets more complicated because it can be like a tiered thing. So like you could have something like, let's see, how do I do this? Something like this that you're moving down, right? So say we're trying to go down over here. Like you now have to ask yourself, now in order to move this one, you have to move these. And in order to move this one, you have to move both of these. And so it only works if like these 4 are like that. So in this case, it's a yes. But like say you have a hash here and like these are empty. Now it's a no for any of those. We shouldn't be able to move any of those because they're like, it's a box, right? And there's some really complicated cases here that you could imagine, right? Where like maybe it like splits out multi-levels and then comes back and splits out. And so it can get really complicated. The easiest way to think about it, at least for me, was to think about it. Oh, I'm sorry, you can't see part of that. I'll move it over. The easiest way for me to think about this is to like just think about it recursively, right? And to say to yourself, okay, well, in order for me to move this block and this block, I have to move all the blocks below it. So I can just recursively check, can I remove all the blocks before it? And then after I've discovered whether or not I can move them all, then I can say yes, right? Only then do I move them all. That's a gotcha too. Like if you're sometimes you may think, oh, I can do it recursively, but if you start moving too early, then you won't. So like you only, how do I say this? You should only move if like all of them can move, right? Like that. Like that's the gist of the gotcha. And so the way that I do that is I just like keep a list of moves. So So I'll have some vector where I say, hey, can I move these two? And it's like, oh, well, only if you can move these two. So I'll go check these. And if these can be moved, I'll then add these to my list, right? I'll add these to my list. And then that will say, hey, yes, these two can be moved. So I'll add this to my list. And now I'll have a list of all these things I can move. I'll do the move all in one batch. And now I can put my at. Now I can move my at sign. Okay? So that's the gist of the day. And again, it's probably easier, at least for me, it was easier to solve to begin with, to simply solve like part one with the O's, and then just like move to part two. Because in part two, you can see there's these cases where you say, oh, this one, the left to right, or the left and right ones, this is the same as P1. You just keep checking left and right. The up and down ones, you now have to like check other side. And this was the hard part, right? Is saying like, oh, I got to check this other side. And so at the time I was thinking, oh, it's just easier to like copy paste, right? And do it. But I was able to merge them together, and I'll show you how it works using a lot of fun Rust stuff like matches and things like that. Again, it's not perfect, but I think it gets there. So the first thing I do is I create an instruction. This is like, will tell me now I can like use enumerations to like an enum to say, hey, do I go up, down, left, or right? You don't have to do this, but it is nice. It makes it easier to check, right? So I just implement a from a character so I can quickly go from one to the other. And then I attach an apply to it that says, like, if you give me the original XY, I'll tell you what the new XY is. Notably, I did not use a graph here for part one or part two, right? I know all the other ones I had points and graphs and things like that. I'm just using a vec grid, right? And so you can actually, I was like, ooh, can I do this without a point? I probably would have used a point if I wanted to like, just because I like points, I guess is the way to describe it. So anyway, we have that instruction, and then now I just need to create the map, right? I want to like this little map over here. I want to be able to say, okay, create this grid and then save all the instructions that are associated with it, right? So that's actually in another part I'll show you in a second. But so how do I do new for part one? Basically, I just enumerate through all of them and add them to the grid. And then if I ever find the robot, I track the robot's position, so it makes it easier for me to do it, to know where it is, right? I don't have to search for it every time. I think this is again, like using it this way is just as fine. I tend to prefer the point because you can do some, you'll see later where I have to pass two values instead of one, or I have to do math on two things instead of one. It's just a matter of opinion, right? It doesn't really matter. Anyway, there's the new for part one. New for part two is slightly different. I still enumerate through all of them, but now if I ever find the zero, or sorry, the capital O, I need to add the left and right parts. And if I ever find the at, I now need to add, an at and a dot. And my robot is now twice as far on the X position. I've been adding 2 for every enumeration. And so I now need to add 2 times that for that enumeration, if that makes sense. So that's just a little gotcha you might run into if your robot feels out of place. It's probably because you need to go like twice as far. And I say all these gotchas because I think I ran into most of these. That's why I'm, fixing bugs and stuff like that. So once I create them, you can see in part 2, or here if I go to the main, again, I'm just like splitting the instructions in half using the split once that we learned about earlier. And then I just create the 2 maps. One of them's using the new wide and one of them's using the normal. And then I parse the instructions just using that instruction from. And now all I have to do is say like, hey, for each of the maps for part 1 and part 2, call apply all. And then once I've figured out what they are, I can just say, what is the GPS value, which is that score that I had illustrated earlier. I can show you what the GPS is. Literally, I just go through all of the values. And if I ever find the beginning of a box for part 2 or the box itself for part 1, I just multiply the y by 100 and add that to the x, and then sum all those together, and that gives me the GPS. But what does the apply all do? So let's kind of step through that. Basically, I just do a for each instruction, call apply. And then, so now we're applying a specific instruction to the grid, right? So we're making some change to the grid. I want to know where I am, like where is the current robot, and where is my next position. So where will the new XY be for the robot? And then I just do some checks, some like high level checks. I say, if the new position contains a wall, I obviously can't move it. Otherwise, if it contains a dot, then I can just swap it out, right? Move it, super simple. Otherwise, I need to try and shift, right? So I should say, so at this point, you can see I've done the I've done the wall, and I've done the free space. So I now know that I have a box in my way. Whichever direction I'm moving, there is a box in the way, and so I need to move the box. So I call this shift function, which moves the box. And then once that shift is done, I can ask myself, well, did the shift work? So is there now an empty space for me to move to? And if there is, then I go ahead and do the move, and I update the robot. So how does the shift work? And this is where we get into the details of like solving it for both part one and part two at the same time. Here's oh, I guess we're not quite there. It's in the can move, because this works actually for both. So what does the shift do is it basically says, hey, can I move myself? Can I move my box and any other parts of myself, or any other adjacent parts that I would need to move? So this can move maybe is not named correctly. It's like can move all type thing, right? It's like, can I move myself? And that can move, you can see down here, it returns, if I can't, it returns none. If I can, it removes all of the values, including myself, that I need to move to make that move possible. And so what happens is I just use the if let sum. So if I can move, I now have a list. I uniqueify it because I think I didn't want to try and dedupe down below. So there'll be some times where I have points that are like move, if in the triangle cases, like these, you'll sometimes it's mostly like when it comes back together like this, like this path will find this box to move, and this path will find this box to move. I only need to move it once, right? So I just uniqueify it right here. So I say, okay, get all my moves and uniqueify it, and then for each of those moves, I just actually apply the move, right? I say, okay, I find where where the new position should be, and then I move I just do a swap here. This is a swap, right? I say, give me the current position and set that to the new position, and set the new position's value to the old position value. So I just do a swap here. And that's all the shift does, right? So I do this recursive call. This can move is the recursive one. And eventually it will either return whether I can move or can't. And if I can, it has a list of moves that I should return. So how does the can move work? This is the part I was talking about where it gets a little more complicated. We have to think about like special cases, right? And so that's where I'll show you what they look like in a second. First of all, I want to get the position of the place that I need to move, right? Get the position of the place I need to move, right? So at this point, I'm like, I know that this is XY is a box, and I know I need to move it somewhere. So where is that place that I need to move it? Is right here, right? And then for part two, I can do an additional check, right? I just say to myself, look, if I'm moving left to right, I can just keep moving all of the characters left to right. I don't have to worry about what side of the box I'm on. But if I'm moving up and down, I now need to find like the other part of the box. That's what this is doing right here. So I say if I have the left side, if I'm the left side, I need to include the right side as well. If I'm the right side, I need to include the left side as well. So I just use this match on my current value and the instruction to say only do this if I'm moving up or down. So if I'm moving right, my other left or right, or I'm in part 1, I've obviously a none. So why does all this work, by the way, is because in part 1 they're capital O's, and in part 2 they're these, and that allows me to like differentiate, right, between part 1 and part 2. Very easy here. So I can just, again, my other is just, is there another side? And in part 1 there isn't, it will return none. And in part 2, if I'm going up or down, it will return these, otherwise it'll return none. So if there is an other, I need to find where its other new would be too, right? Just like I got the new X and Y up here, I need to know the other news X and Y as well. And so I just call this map function. You can call map on a option, and if it's none, it returns none. If it's some, it will call this function, and so I just call apply on it. So now I do the base checks again. So here's another, I do another match, and I say I do a match. How do I say this? I do a match on the new value, so the value that I'm looking to move my box to, or like my current box to, and then I also want to track the other box and the other new, or the other part of my box, and where the other one would move as well. So this first part just says, are either of them a wall, right? Obviously, if it's a wall, I can't move it. And so this is kind of it. I realize the syntax may look a little strange, but it's basically just saying, is the new place I'm moving to a wall? If so, I can't do it. Otherwise, do I have some other part of my block? Do I have some other part of my box that I need to move? And if so, is the place I'm moving it to a wall as well? And if that applies, then I also return none there. So this is just the case, again, to highlight that essentially what I'm doing is, right, in part 2, I might have this, and I might be here. I need to make sure that this is not a wall and this is not a wall. So both of them are the case. So it's an and, right? Not an or. Both of these have to be movable. Otherwise, I can't move it, right? In part 1, there is no other, right? So I just have an O. And obviously, I can just check this one. And so that first section checks this part right here and this part right here. And that second one says, if there is this right here, also check it, okay? So that's what these two are doing. Then I can ask myself, am I free to move, right? So what does it mean to be free to move? Like, can the box be moved? Are there dots above the box, right? And in the case of the O's, that would be where there is no other and I get a dot. Then, of course, I can just move it by moving myself, right? If there's a dot here and I have the other part of my box, so this is like part 2. So if I have a dot on my side of the box, and there's another side of the box, if that part is a dot as well, then I can include myself and that other side. Does that make sense? Hopefully. It's like this is the case for part 1. This is the case for part 2. For part 1, I only need to check 1. For part 2, I need to have a dot and a dot in the other position. And if that's the case, then I can move myself and the other side of my box. Okay? So these are like the base case checks of, can I move at all, or am I totally free? And so after I've done these checks, there's only one other situation, is there's some box in the way of me, right? So I'm a box, but there's some other box that's in the way of me. And so you have to ask the question, well, can I move the other box, right? So we're going to track. So we just call can move recursively is probably the easiest way to think about it. And you can see it right here and right here. So I have to do it twice because obviously I want to move both sides of the box for part 2, but only have it apply for part 2, right? But I do want to track all my moves, and so that's why I create this vector here. I say, what are all the moves I have to do in order to make it so I can move my current box? and I just have to ask I say, okay, well, if my new position doesn't have a dot, I already know it doesn't have a hash, so this one needs to move, right? The question that I'm essentially asking is, if I look like this, um is this one a box, right? Is it like this? Is this a box? And if this is a box, I know I need to now call it on. I need to try and move this one, right? So I call can move on it, and it will return, right? It will do its recursive thing up here, and it might return true, right? And say, yeah, I can move all this stuff, and now I'll add all those to my list and recursively add them to this list, so I know of everything I need to move. Obviously, if it returns false, I know I can't move anything, and so I just return none, right? That's what this question mark operator does. I call can move on it, and then I kind of unwrap it, is the way to think about it. So I take the option and I say, if it is some, I can just extend it with the whatever's in there. Otherwise, this question operator returns none, which is what I'm expecting to return here. And then again, I just have to do it to the other side, right? So I say, hey, is the other side of my box, this won't apply to part 1, but it will apply to part 2. Does the other side of my box have a dot? And if it doesn't, I need to do the same thing, right? It just with the other side. So I realize this may look a little confusing, maybe, but it's mostly just to say, like, hey, look, I was able to make it so I can solve both part 1 and part 2 at the same time. There was enough overlap that I thought it might be fun to try. In hindsight, it might be easier just to do it separately, at least the way I have it written now, because you're doing enough of these if checks that it may feel confusing if you don't understand that you're solving both part 1 and part 2. Like if I was writing this actual code, I for like someone to review, and it was going to go in a program that was going to be there for 20 years, I'd probably duplicate the code where I could, and or maybe write some functions to help with the duplication, just so it's easier to grok, right? So anyway, but you can see here, like I'm just doing, I'm moving the left side, or I'm moving my side of the box, and then I'm seeing if there's some other side that I need to move as well. And if there is, I check if it can be moved, and if it can, I add that to it. So now I've moved all these other pieces. If they both return true, right? Or okay, or some, I guess technically, if they both are true, yeah, I can move these, and I've extended them. Now I know I can move myself, which is this, and for part 2, the other side. And so after I've done that, I just say, okay, yeah, I can do some of, in order for me to move, I can move these 2 pieces, but in order to do it, I also have to move these pieces as well. So that's it. That's part 1 and part 2, and you can see it runs pretty fast. I don't know that we'll go look in a second. Doesn't really feel like there was like any optimization things or anything like that. It was really just like, can you figure out the weird corner cases, and can you solve it? In that respect. And for me, it felt like a very recursive solution. Is like you're again, the high level way to think about it is, if you want to know if I can move this one, you just have to ask yourself, well, can I move this one? And you do that recursively. Eventually it works, and then you can move them all, right? It gets more complicated in part 2 because now you have branching, right? You have to both be able to move the left side and the right side, and those branches can go quite a bit, right? So you can imagine it going deep, but it's not like you're moving a million things, and so recursion felt like a good way to do it. So there you go. That's my solution. I thought it would be fun to go see what other people are doing or saying about it. I don't think there's anything else I wanted to talk about. No. You can see for the puzzle input, it's much longer, and there's substantially more moves, which made, like, there were a couple times when I was like, oh, I kind of want to see why it's failing, and so I was trying to debug it. A lot of these moves tended to be no ops, and so it was like very skipping around trying to find the right place was a little bit hard, but anyway. Okay, let's refresh, see what we got here. It's time for your daily 2D simulation puzzle. Yes. We have had a lot of 2D simulation stuff, right? I agree with that. There's been a lot of 2D stuff that we've had to do, but it's fun. And I tried it a different way. Sometimes that can be fun too, right? If you've been doing it one way, maybe use another data structure. Try a new data structure, one that you haven't used before, and see how it works for you. So, anyway, yeah, that's true. I've had enough. I'm taking control. Well, that's kind of fun to see the graph. Oh, that is cool if you can take over and start moving it yourself. That's pretty fun. Hey, yo. Okay. Burn the robots. Burn them. Oh, that's kind of fun. You give it some instructions and Bob as you. Very cool. Oh, that's very cool. I'm not smart enough in Minecraft to be able to do these things, but that's awesome that you could do something like that in Minecraft. Part easily my favorite part 2 so far. Let's try. I was really not a fan of 14. So the previous days, most people, or I don't know, some people weren't. Yeah, it was a good logical progression. I do agree with that. Like you definitely go from like, okay, here's how you do it. Now I'm going to add some complexity to that, and those are always there's different ways to like think about part 1 and part 2. And so this is a pretty common one, is to say, oh, now there's additional complexity you have to handle. There's other days like yesterday when it was like they're not really the same. I guess we looked and they could potentially be the same because the safety factor from the previous day ended up helping you find the tree. But there's days where like it's like, okay, it's more complex, so can you figure it out, which was today. There's also days where it's like, oh, now I'm going to make it impossible to solve with brute force, so you have to come up with like a more efficient solution. Those days are fun too because it's like, okay, how do I optimize? So yeah, I could see part 2 being fun. Wasn't my favorite, I didn't know. Oh, this guy didn't notice it could be done recursively. I mean, I suppose you don't have to recurse. You just keep checking and tracking. I mean, you've got to keep some list somewhere where you're checking and tracking and eventually get there. So you probably don't do recursive, but you do it in a for loop. Well, maybe we'll see his code. I don't see a lot of craziness. A second robot has started malfunctioning. Okay. Lots of terminal emulators. The map is actually pretty big, but you could probably still fit it in a terminal, right? Well, you might have to rotate it for our wide screens, but it looks like most people didn't have any substantial problems with it. You'll notice like the previous day doesn't have a lot of like graphs and visualizations as compared to today. So I'm guessing that like there's that's probably a signal that it wasn't as hard, if that makes sense. Yes, we are back to the for loops. Yeah. Recursion, that worked too. Okay, there's a lot of people that did simulations. Again, that's probably a sign that it wasn't that hard. Debugging part 2. I don't know what this meme is, but I presume it's like not easy to debug. It is really hard because if your part 1 worked but your part 2 doesn't and you have the test cases, like the simplest test case only has a few moves, so you could probably like step through it. But the other ones have like relatively large moves and they don't present themselves. Yeah, okay. Yeah, well, I was trying to figure it out. I had these problems where I was just moving one piece. For some reason, it wasn't seeing the other piece. And I think it was because I was mixing up my X and my other X's. Okay, we got a lot of visualizations. Maybe today's reviews won't be hard because most people are just visualizing the changes, which is fun, right? Like if you have time, you now say to yourself, "Oh, can I visualize it?" I took the approach of, "Can I try and optimize both parts?" I got scared for a minute. Everyone today reading the prompt. School of Lanternfish. Okay, there is some lore behind Lanternfish, and so I can see why that might. Uh, I think it actually had a link here, so you can go look at it. Bada bing. It was like the expansion one. Yeah, they're like spawning and growing, and there's like some definitions for how they spawn. I don't remember what the gotcha was that made it so hard. It was just like because of the exponential growth at 250 days, it becomes really huge. But I think there's a. I don't remember. I'd have to go look at my solution. I think there's a cycle to the cycle and what you had to do. I don't remember being particularly angry at the lanternfish, but it's possible I was at the time. Okay, 2021. I definitely solved that one. I don't know if I was doing videos then, but I definitely solved it on the day. Okay, this person's having a problem. Let's. Oh, it's resolved. Yes. Yeah. So he's asking like, "Hey, okay, because it's empty here. Can I move them all? But what if only one of them is blocked? Can I move them all?" And like, you can't. You have to think about the chain is like this box is trying to move this box is trying to move this box, but this box can't move because it's stuck. So since this box can't move, none of them can move, right? So there is that's what made it recursive for me in mind was thinking about it that way. Okay, let's just spend a few minutes going. It didn't seem like today was a particularly crazy day, so there's not a lot of discussion of like how do you solve it or whatever. Let's just go look at some solutions. I mean, it sounds like he did the same way as I did. I don't. My way is not particularly ingenious. It's just yeah. Okay, yeah. Oh, this is interesting. Yeah, so you can kind of track. You can say like, oh, if I have this, I now it's two values. If I have this, it's one value. And so I just have to. That's an interesting way to solve it, right? Is now each coordinate is like how do you say this? Each coordinate on the map is like quote unquote linked to a set of coordinates or a list of coordinates. And so for these ones, it's a list of two, and for these ones, it's a list of one. And so you just because you can do this, you can just check in all of them. This is probably a cleaner way to do it, I imagine, which is kind of interesting because then you already know you've like think about like you've built a graph of like the tree of the boxes that need to move that are adjacent to it, and you can just kind of like loop through those. So that's a cool way. That's an interesting solution. Dart, go. Should we see what the go one is? don't think we've done Go in a little while or looked at some Go code. These are just helper functions so far. Yeah, so we're just turning, yeah, these are all helper functions so far. Parsing from an action to a move. Parse the grid. Parse wide. Yeah, we had those. Warehouse. Okay, some print functions. Move. Okay, my initial solution had this too, a move horizontal and a move vertical. Again, because the move horizontal is simple both for part 1 and part 2. Is the vertical that's more complex, right? Which I presume, yeah, you can see here is like in his code or their code, the horizontal is pretty easy because you can just kind of keep moving to figure out how far you need. Keep going down that way to figure out. The vertical is harder in part 2 because you now are branching, right? That's the high level way to think about it. Doesn't look like it's being done recursively though. It looks like he's keeping a list. You have these. And then, so like basically he's adding each one to the list and then seeing it and then checking that list, seeing if those need to be moved until he gets to the end. Y equals 0, y equals height. That's kind of interesting. Okay. Excuse me, nothing crazy on that one, but very cool to see it in Go. Do we want to see it happening in C? Okay, so for the move function, you determine where it needs to move, like the delta, and then you increment those. You check if it's used. Otherwise, if it's not, you do a swap. Yeah. So the nice thing about like Rust and Go and more modern languages is you can do this swap in like one line. But I mean, you know, there's nothing wrong with this swap. It's all fine. Okay. Yeah, nothing crazy about that part 1. I don't know if I want to particularly read part 2. Yeah, can move vertically. So there's a lot of these where it's like, you know, this is, I think I kind of did this first, is like, can I just move it vertically? And then if I can, I do the actual move. It was easier. I mean, I still technically do that, right? Is like this can move kind of returns whether or not it can. And then if it can, it returns what needs to move or what needs to move to make it move. So I can't tell really here. Let's look and see. Yeah, he checks first and then he does the move. And if he gets any of these, he tries to move move the opposite side of the box as well, right? Which is okay. I don't think I mean, technically mine's more efficient dish because you're like recursing here, and you're recursing here. You could potentially do it in one. I don't know how that looks in C, but it's solved the same way and it looks great. I think this looks fun. I don't necessarily like the syntax from C. I'm used to another kind of style from C, but it looks okay ish. not as many. I don't know why. Why do I like so many spaces? You've probably seen this in my code. I use a lot of spaces and like break things into paragraphs. People have different opinions about that, so you'll have to let me know what your opinion is. Do you or don't you like it? Let's look at this Rust one. A point. Haha. Got him. Yeah, I just tried not to do it as a point. Tile. Okay, yeah, you could have also done the tiles as an enumeration. Then you could ask questions like, you know, is it some tile box left? So in my code, I actually do like the, is it this character? Whereas you could represent it as tiles and that make more. Just to be clear, I would probably, if I was actually writing it, I intentionally didn't do it this way. So they're using points, directions, and other enums. The question of like when and how many enums to use is kind of left up to you, right? But like, I tend to prefer more enums because it often simplifies some of your code. Like for example, in my code, you'll see me doing a lot of like otherwise it's none, otherwise do nothing. Like sometimes when you're using enums, like you could like fill this out appropriately, I guess is the way to say, or fill it out all the way without having to go through it. But let's see what happens here. It doesn't look like it's technically recursive. It's using a stack, right? So it's tracking the moves you have to make, and then it's keeping a queue. Oh, how do I say this? It's, you can think of it as doing like a BFS is what it is, right? It's doing a BFS of the moves. If we ever hit a wall, we break. Otherwise, based on the direction and what's in that direction, I can, add it to my list and process it. That's a cool way to do it. You basically do a BFS of all the things you need to move, and if they're all able to be moved, like once you get to the leaf nodes of the BFS, then you can do all the moves down here. Very cool. That's a fun way to solve it. Cool, cool, cool. Cool, 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 cool. We haven't done a lot of C++. Should we go look? Okay, we just got some helper functions so far. Well, this is kind of interesting. I think we've seen this before in like some Python code where it's kind of saying like, is it a direction line? And if it is, parse the line for directions. Otherwise, it's like part of the puzzle. And if it's a new line, you just skip it. So the idea is like these are all, because it has a hash, it's not a direction. But like once you get this, you say, oh, that's a direction because it's not included as like one of my things. So then you can just like slowly push all of them into their thing. So by all of this is just kind of setup code. He does call find robot. You could potentially do the find robot in here. But I mean, the problem is like you're pushing. Oh no, you do turn them into tiles. Like the character right here, so you could potentially say if it's a robot, I'm going to return that as well. Uh, or include it in your map, I guess. What does his map data structure look like? Did I miss it? Am I blind? It's just a vector of vectors. Okay, so you could do this. You could do this up here too, right? So you could just say, "Oh, I also know the robot's position. I'm going to push it in there," but that's okay. Move. Let's see what's going on here. Oh, this is kind of interesting a little bit. It's like the double wide tiles are being represented by a single data structure, but it contains both of them. I mean, that is definitely. I guess I've been looking through these too fast. You could definitely treat this as a graph and like bring the nodes together, right? So imagine your graph is like, okay, here's a box, so that one's linked to this. I didn't do that right, but that one's linked to this box, and it's linked to this box. So you now know, like, if you're moving this one, you have to move these three. So what are these edges? It's like the edge here is up, the edge here is up, but it might have other edges too, right? Presume there's some below it. You might have another edge that says, oh, for down, it's just one block, and for right, it's this block. It'll only ever be one for right. But like you can imagine you're like building this graph, right, that does these things like this, and now you have this network. So the question is like, what do you do when you make a move? You now have to like adjust the graph for this, right? So if I actually, like, say I move this one over here, that like takes it off of this one right here and maybe puts it on another one. I don't know if I like that. That's not what he did here. Yeah, I don't think he does that here. He's basically just using the D tile to contain like both of them is what I gather. Okay, I haven't seen anything that's pretty crazy of like here's how you solve it. I think my guess is a lot of people have done kind of the same thing. Is they've said, "Oh, I need to move blocks around, and can I move blocks around in a way that handles all the special cases?" Like that's how you had to solve today's problem. So, and it just made part 2 made that movement more complex, substantially more complex actually, right? Because before you could do just like a simple line one way or the other. Now you have to branch, and so you had to think about it another way. Like do a BFS I think would be a good way, like we saw in some of the examples, or do recursion, which is what I saw. I think most people did them either of those ways. I didn't actually see any of the code where someone was actually like not doing either of those. So, but it was suggested in one of the previous previous posts. Anyway, very fun day, not too tough. It gave you a lot of time if you dedicate some block of time to do some special stuff with it. So I'd love to see if you made your own visualization or how you did it. Send me those things, and I'll check them out. I'll respond, and we can highlight some of them maybe as we get through the days. I usually like when it's over, maybe we do some recaps and clean up code and stuff like that, so you can see how things changed. I'll keep your solutions in mind, or I can showcase some of the things you did. So anyway, We'll talk to you tomorrow. Hope you guys all have a wonderful day, night, morning, evening, future, wherever you are.